Welcome everybody to this talk about modeling the effects of storms on thermal structure, nutrient distribution and phytoplankton growth in lakes. My name is Jorrit Mesman. I'm a PhD student at the University of Geneva and Uppsala University and part of the MANTEL project. So wind affects lakes in multiple ways. It mixes water layers, which causes cooling of the surface layer, partially by this mixing, partially by simply colder conditions that are often occurring. It can bring up nutrients from the hypolimnion, and it can also deepen the mixed layer, as you can see in this heat map over here, where there's clearly a deepening by several meters. And in shallow lakes, there can also be resuspension of sediment. And the overarching aim of my PhD is to assess how the response of nutrients and chlorophyll to storms changes with climate warming. So how do they respond to storms and how do they recover from it? And if we try to link the effect of wind on phytoplankton growth, we quickly get a quite complicated figure. As wind stimulates mixing, nutrients are mixed into the photic zone, which can boost phytoplankton growth. But as the mixed layer is deepened, there's more light limitation, which can have a negative effect of growth. And then there's water temperature. Water temperature can affect growth rates, maybe negatively for phytoplankton. But then if it has the same effect on zooplankton that predates on phytoplankton, the effect can be both ways. And there's also different timescales involved. If anoxia decreases due to a storm, as oxygen is mixed downwards, there is maybe less nutrient release, so less nutrients that end up in the photic zone, but on a different timescale. And there are functional traits of phytoplankton. Maybe some phytoplankton does well under dark conditions. And then there are factors such as lake depth, time of the year, trophic state. And we also want to bring in climate warming to this schematic. So it becomes very complicated very fast. And this is where coupled physical and biogeochemical modeling can maybe be an outcome, as you can still quantify, or you can try to quantify the net effect of many of these antagonistic processes. And you can do climate forecasts. The first part of this presentation, I'll show that we validated some physical 1D lake models during extreme events. And in the second part, we try to figure out what are the main causal factors that cause phytoplankton to either increase or decrease after a storm. And because before we apply these models, we need to know how well they perform. And this is what we did with these physical models. And although we are also interested in the biogeochemistry, it's essential to get these physics during storms right, as water temperature, mixed layer depth, and mass transport of nutrients are essential to know how well phytoplankton can grow after a storm. So for this, we did a model validation study in 3 lakes, Loch Via in Ireland and Loch Erken in Sweden, which are both deep lakes, and thirdly, Müggelsee, which is a shallow lake in Germany. And we fitted 3 different one-dimensional models, Simstrat, Gotham, and GLM, and we forced them with high-frequency data and also validated them with high-frequency data. So if we look at the results, and on the y-axis you see the change during the event in surface, volume averaged, or bottom temperatures, Schmidt stability, and mixed layer depth. And in white, you see the observations, and the colored box plots are the models. So the overall trends are simulated rather well by the models. There is a decrease in surface temperature, increase in bottom temperature, decrease in Schmidt stability, and an increase in mixed layer depth. This is the results for Lake Erken, so it's a deep lake. So they are simulated rather well. There was not much over or underestimation by the models, and the timing of the events was right too. However, if you look at the mean absolute error, so the uncertainty of your simulation, we found that in the deep lakes, this tended to increase, so you're less certain of your prediction. But in Müggelsee, the shallow lake, because the storm always caused completely mixed conditions, the model actually predicted water temperature slightly better. So it's important to keep this in mind. And if you're interested to read more about this, the study got recently published in Environmental Modeling and Software. So this brings us to the second part, where we move to biogeochemistry. Then if we assess literature, there are very diverse responses of chlorophyll to storms. Some studies report a very big bloom after a storm, while others don't see anything or even a decrease in chlorophyll. And this is partly due to these antagonistic processes, notably the upwelling of nutrients versus the deepening of the mixed layer. And we use the Gotham-Selma model, which are coupled with the FABM framework, to do a quantitative comparison. So Gotham is the physical model that I mentioned in the first half of the presentation, and Selma is a biogeochemical model which has nutrients, some phytoplankton groups, zooplankton, detritus, and oxygen, includes some bottom processes like burial and phosphorus release, and essentially under influence of light and nutrients and temperature, phytoplankton can grow and might be predated by zooplankton. When they die, go into a detritus pool, and then the nutrients may get recycled. This is still work in progress, so the results you're about to see might not be the final results we end up with in a publication. We run a simulation for Lake Erken, one of the lakes we included in our previous study. We used 20 years of data. Lake Erken is a rather big lake and is stratifying a maximum depth of 21 meters, and it's mesotrophic. These are some figures for the calibration and the validation. As you can see here, temperature is done rather well. In the first 18 years, the red dots are the observations, and the black line is the simulation. It's done rather well, and in the validation period, the blue dots as well, with the root mean square error slightly above 1 degree Celsius. Oxygen, this is 17 meters depth. In summer, there's a drawdown, anoxia has formed, and this is simulated rather well by the model. However, in winter, there can also be low oxygen conditions under ice, which is not reproduced by the model. But in our study, we focus on the summer periods, specifically July, August. So this is not too important. For nitrate as well, the fit during summer, so there is nutrient limitation, is done rather well. But winter concentrations tend to be underestimated, and the timing of all the processes is also not correct. So we're still trying to improve this. Similar story for phosphate. Again, in summer, there is nutrient limitation, but winter concentrations are underestimated by the model. And also in these 4 years, the model sort of loses track. So this is another thing we want to improve. And then the thing we're mostly interested in, the chlorophyll. Chlorophyll in Lake Erken shows 2 distinct peaks every time in spring. There's a spring peak, and then in summer. And this happens almost every year. And the summer concentrations are reproduced rather well by the model. The model is very close to the observations. But in spring, model definitely underestimates, which may be caused by under ice dynamics that are not reproduced by the model. But again, we are mostly interested in summer conditions. And we still hope to improve this. So the first step of what we want to do with this model is to discover what are the causal factors. And we do this by making a block design with wind speed, mixed layer depth, solar radiation, and hypolymnetic phosphorus, plus 2 other variables that we have not done yet. And there are 10 levels for each of these variables, which we base on observations. And then we run 1 simulation for each combination. So a total of 10,000 simulations. So how does that work? We start simulation, start of July, and then after 2 weeks, we induce a wind event, a storm, which is over here with varying intensity. And then we assess what is the average chlorophyll level in the top 6 meters over the next week, and that value we store. And then you get a graph like this. So what you see here with the colors is the relative increase in chlorophyll as relative to the column on the left here with the lowest wind speed. So what you see here is that for shallow mixed layer depth and for moderately to high wind speed, there is a strong increase in chlorophyll. And if we put that with all the other scenarios, so higher hyperlimnatic phosphorus when you go to the right, higher incoming shortwave radiation when you go down, we see that this pattern actually is very consistent. So for low mixed layer depth and moderately to high or high wind speeds, there is the most increase in chlorophyll. Now notice that there is almost always an increase in chlorophyll, which shows that nutrients are limiting in these simulations. This is why we also want to do the other simulations with lower amount of nutrients or with more amount of nutrients. And we have already seen that when nutrients are plentiful, there can actually be a negative effect of a storm because of this deepening of the mixed layer. If you initialize with a deeper mixed layer, the storm has less effect, which makes sense because less nutrients can be mixed towards the photic zone. And there's also a weaker effect on the mixed layer itself. And we still want to add simulations with different epilimnatic nutrient levels and with different surface temperatures, which indicate strength of stratification. And then we want to do long-term climate simulations where we feed the input of a regional climate model into our simulation so that we can see what kind of effect does a longer period of stratification have, for example. And that concludes this presentation. I would thank you very much for your attention. And if you have any questions, please do not hesitate to ask them. Thank you.